Okay, thank you. So this is the final talk of the summer school, so I'll be brief, hopefully. I don't know, hopefully I'm not boring everyone, but where are we? So I wanted to talk about formal verification of cyber-physical systems. And the way we're doing that is we're using flow pipe construction, which is one method, not the only method. And with flow pipe construction, we have this standard algorithm. We're doing set-based reasoning. In that standard algorithm, we have operations on sets. And so you have certain operations that you want to do on sets. And in order to efficiently do these operations, we have different data structures. And depending on the data structure you use, you'll have different complexity of these operations. And so far we've talked about vertex polytopes, which is one data structure. It's not a good one. And why isn't it a good one? It's because it has this exponential scalability. As you go to larger and larger dimensions, your computation time increases to the point where you can't analyze larger systems. So the first sort of better data structure we discussed was zonotopes. So zonotopes are sort of the first one that was introduced that sort of scaled better, right? So this is in the 2000s, I want to say. And you have this nice operation where you have generators, and then it becomes sort of this time elapse for a zonotope is linear in terms of the number of dimensions of the system. They do have problems. They have sort of, they're centrally symmetric, right? Intersections are more difficult with zonotopes. So then there's support functions, which allow you to look at the time elapse of an arbitrary convex set in particular directions you care about. So support functions also have problems. So one thing we mentioned is we have to compute this matrix exponential, which can be challenging in high dimensions. There's also issues with intersections as well, and aggregation. So the last data structure that I'll introduce here is a generalized star set, and then a specialization of that called a linear star, and that's what we'll work with. And then for the rest of the talk, I'll show you basically some of what I think are the state-of-the-art tools for reachability analysis with flow pipe construction. And then maybe if we have time, we'll talk about model transformations. Essentially, the methods I've described in detail anyway have dealt with linear systems, but you might be wondering, not all systems are linear. Do we throw everything away? And the answer is no. Actually, you can do transformations of nonlinear systems so that these linear methods can still be used to do formal analysis. So let me talk about that. So this is the definition of a generalized star set. It's a newer data structure. This is 2016. It was introduced. It's a little bit more complicated than the previous ones. I'll say here that it contains three parts. There's a center, there's a set of basis vectors, and there's a predicate that you evaluate. And it defines a subset of the real numbers. So it's a subset of r to the n. So it's a set of states. And I'll go into this with illustrations a little bit more, but it's still defining a set of states. So before I do that definition, I'll have a sort of a short quiz on superposition. So generalized star sets do reachability of linear systems, and they rely on superposition. And so here's the first question of the quiz, right? So if I had a 2D linear ordinary differential equation, x dot equals ax, and I told you initial state 1, 0 goes to state AB after 10 seconds. And then I ask you, where does state 2, 0 go to after 10 seconds? Linear systems have something called superposition, which means that you could immediately know that the answer to this question is 2A, 2B. Because state 1, 0 went to AB, state 2, 0 goes to 2A, 2B. So there's a scaling property. The second question is, if I had the same system, and now I told you state 0, 1 goes to state CD. So now you have two pieces of information. You know where state 1, 0 goes, and you know where state 0, 1 goes. And I wanted to figure out where state 2, 2 would go after 10 seconds. Because of superposition, you could immediately know the answer to this question is just sort of a combination of this state and the state that 0, 2 would go to. So it's 2A plus 2C, 2B plus 2D. So this is sort of a line segment, right, in 2 dimensions. And so that's great for individual points. What if we were doing set-based reasoning? What if we're worried about sets of states? So again, new system, state 1, 0 goes to state AB. Where could any state x naught 0 go to if x naught is in the state 3, 5? Right? And so again, because of the scaling property, you can sort of intuitively say that it's anywhere between 3A, 3B, and 5A, 5B. Now, so this is actually the line segment. The previous one was a point. So, but this intuition sort of tells you that, using information about individual trajectories, you can actually derive information about where sets of states will go to. And that's sort of what we need for reachability. So superposition means you have the scaling property as well as sort of additivity properties. So what is a generalized star set? I mentioned there's 3 parts. There's a center, some set of vectors V, and a predicate. And the way it defines a set of states is sort of as follows, but sort of easier to look at the example, I would say. So here's a generalized star set where the center is the origin. The set of vectors are the unit vectors in the directions of the axes. And the predicate is a predicate on basically given the multiple of each vector, does that vector satisfy, do those multiples satisfy a certain property? So in this case, if you take alpha1 times v1 plus alpha2 times v2, add the center, you'll get a point. And if alpha1, the absolute value of alpha1 is less than 1, and the absolute value of alpha2 is less than 1, then we're saying this state is in the generalized star set. So for example, this point, there's a certain value of alpha1 and alpha2 that satisfy this equation. Those values of alpha1 and alpha2 are both, their absolute values are less than 1. So therefore, this point is in the generalized star set. So we can define now a set of states in this way. We can change the predicate and get more complicated sets of states. So here, again, we have the center at the origin. We have the vectors are these unit vectors aligned with the axes. Yes, sure.
So you had some constraints that, so V alpha are the same number as the dimension. I thought that in the previous slides you had that.
Let's see.
That you had m vectors of n dimension. Yes, so you have m vector.
Yep. So there's m of these vectors, and each of the vectors is in Rn.
So they've expected then V alpha should be m rather than n.
Then n. OK, yeah, maybe I switch these two around. So the number of alpha needs to match the number of vectors, right?
So it should be m, right?
This should be.
I should range from
yeah,
1 to
yeah,
n.
yeah. That should be an m. Yep. Because.
Then the predicate should be over R of m.
Yep.
Okay.
Exactly. Yep. Yep. So yeah, the dimensions are different, right? So you don't necessarily. You can have more of these vectors than dimensions or less. So this was a set of states for a particular predicate. If we consider a different predicate, we'll define a different set of states. So here it's the same predicate. The absolute value of alpha1 is less than 1 and absolute value of alpha2 is less than 2. And now we have this extra part, which is that the absolute value of alpha1 plus alpha2 is less than 1.5. And we can see we've now got a more complicated set of states. We've defined an octagon, essentially. So you can define nonlinear constraints as well. You could imagine you have a different type of predicate, and now your set of states is this nonlinear sort of set of states is no longer a polygon. That's possible with generalized star sets. You can have very intricate functions on your predicates, right? If you really wanted to, you could define this non-convex shape even as your predicate too. And similarly, you could define a set of states using generalized star sets. Reachability. So once you have generalized star sets, yes?
It can also be disconnected, right? You could have also disconnected sets.
Yes, if you want to, you could define a predicate like that, so you could define a set of states like that, yes.
Yes, I don't understand the shape of your set. It's not a star, because the name star doesn't mean that it is a star-shaped
No,
set.
So I didn't make up the name of the data structure, but it doesn't mean it's a star in the sense that, let me see, there's a center, and there's generally you stay around that center. But it's not a star in the traditional sense where it's some sort of spikes around a point.
And when you write P of alpha equal to top, top means true, no?
P of alpha, so it's
alpha bar equal to.
Yep. So this is the set of states where the set of states X where the predicate evaluates to true.
Okay, and can you show us a set which is not a star?
Star
set.
I don't know. If you can define the set of states using a predicate, I mean, it depends how complicated your predicate is.
Well, if the predicate says that the absolute value of alpha is 1, it means that you just have 2 points, so they are disconnected. And
That would be a disconnected set. Well, what's the question?
So can you give us an example of a set which is not a star set?
Which is not a star set.
no,
A donut. So you could define the sum of the predicates is within some range, and that would be.
There is no set that is a generalized star set if you don't restrict the predicate definition, because you could always say it's generated by some arbitrary nonsense of vectors and so on, and then the predicate filters out, the numbers whose Turing machine Gödel encoding halts when run on input something crazy. So it really very much depends on what the predicate language is.
Yeah, so you're kind of pushing the complexity into the predicate now too, and so it's a good point that if your predicates are very complicated, you can define the set of states possibly, but can you reason about them is another question, right?
Okay.
So what's the reachability algorithm? So it's pretty simple actually. It's if you take a generalized star set defined in this way, you simulate from the center. You simulate from the center plus each of the vectors, and then you get a new center and a new set of vectors defined by the sort of the difference between the points. You use that as a new generalized star set with a new center, a new set of vectors, and the same predicate. And you'll get the time elapsed version of that generalized star set. So again, this still doesn't solve the problem of if your predicates are very complicated, you might not be able to reason over them. You need to find these alphas. You need to find points where there exist alphas, and the alphas need to satisfy the predicate, right? So a specialization of generalized star sets would be linear stars. And those are simply generalized star sets where the predicates are limited to be conjunctions of linear constraints, so polytopes, basically. When you have these types of predicates, you can use linear programming to do containment checks. And so linear programming is fast and it's scalable. And the advantage is this creates sort of a very nice reachability method, because really what are we doing? We're doing, for an n-dimensional system, if we start out with the vectors are the unit directions, then you have to do simulations, n simulations, maybe +1 for the center. Then you solve a linear program, and then it directly tells you if an unsafe state, which is defined by linear constraints, contained in the generalized star set. That's only true if the linear program is feasible. So I'll have a demo of that as well. Let me do that now. Okay, so let's save this. Okay, so this is a demo for generalized star sets and reachability. It's JavaScript, so you can go online and play with it yourself too. StanleyBak.com/HighLow/demo.html if you want. So this is a vector field in 2 dimensions with a set of states. If I look at my differential equations, it's the same ones I think Andre had in one of his examples. It's a harmonic oscillator. So the trajectories will rotate around the origin. Okay, if I look at this set of states, and I wanted to see how is this defined in terms of linear constraints, you could create a set of linear constraints that exactly define this set of states as follows, right? So in this case, I have initial conditions. So my x is between -3 and -2. Similarly, in this set of linear constraints, I have these x naught and y naught variables. And if you do the matrix multiplication, you see that x naught is greater than -3. Y naught or x naught is less than -2. You can change these initial conditions too. So if I move these, you can see that by changing the set of linear constraints, I now have a different set of initial states, right? Similarly, if I move everything around, that corresponds to just moving the linear constraints around, these 4 values. So these constraints define the initial conditions. This set of variables is x and y, so that's the values of x and y at the current time step. So initially, you have an identity, basically. The values at the current time step are equal to the values at time 0. And so that's why you have these two lines basically saying this is x is equal to exactly x naught, y is equal to exactly y naught. What this set of states, these two values are, this is the set of basis vectors, those ones that will change over time. And so this column corresponds to this point initially, and this column corresponds to this point. So as we move forward in time, you can see that the simulated points have moved forward. We've updated this basis matrix inside the linear program, and now the set of states represented by this set of linear constraints is now this time-elapsed green box, right? You can see as you move forward all the way, as the simulations work their way all the way around, you end up back at your initial states, and that's sort of what you'd expect. If you change your dynamics, you could think of using something like a damped oscillator. So now these are no longer zeros, but there's damping. And you, let me see, move forward in time. The set of constraints you had are the same, but now the simulations evolve differently. This basis matrix is different, and now you have a different set of reachable states. And you can play with this a little bit, like moving around the initial states. You can see how that changes the reachable set of states at a particular point in time. But notice now I'm not updating the basis matrix, I'm just updating the constraints on the initial set of states. So you can imagine the reachability algorithm now, right? You take an initial set of states, you run n simulations, n+1 simulations, come up with a basis matrix, solve a linear program. Then evolve all the simulations for one more time step, solve the linear program again, and keep doing this over and over. So there's a couple optimizations you can do that are fairly important for timing purposes. One is if you're doing this one step at a time and your time steps are small, the linear programs are actually very similar, right? So if I took this linear program and I went back, a couple hundredths of a second, it's almost the same thing as the previous time step. So the solution to the linear program is likely the same set of constraints that you had before. So with linear programming, there's something called warm start with linear programming, where you give it an initial feasible solution and it works off of that. So the way simplex-based linear programming works is first it tries to find a feasible solution, something along a polytope, and then it'll optimize that polytope according to your constraints. If you have a solution from a previous step, you already have a point on that polytope. You just have to optimize it. And a lot of times the optimal point is the same optimal point that it was before. So the linear programming step almost becomes free at each time step. There's a very small amount of additional work you have to do compared with the previous time step.
Excuse me?
Yes?
On the simulation, what is the new identical center here?
Am I sorry?
What is the new identical center? New center?
OK. So here I had the center at the origin. And then if you have a linear system without an affine term, so x dot equals ax, then the origin just stays at the origin. Yeah, so you didn't have to worry about it in this case. Yep. So this is the case without any inputs. If you have inputs, remember we had this formula. So this is where inputs are fixed over time. So what is this really? This is a time elapsed times a set of states. Each term of these is really a time elapsed times a set of states. This is it's a different set of states, but it still ends up, it's still a set of states. So you can just use the same reachability algorithm you had been using for an initial set with sort of this different initial set defined by you and compute what this term is. So each of these terms we can compute with all of the existing algorithms we've had before. The difference now, though, is when you want to compute sort of the combined set of states, you need to support this Minkowski sum operation. And so it turns out for linear stars, you can do Minkowski sum, and it's pretty simple. You add the centers together. You take the basis vectors from the first star and the second star. You sort of put them together, so now you have more basis vectors. And you take your predicates and you take the conjunction of the first predicate over the first set of vectors and the second predicate over the second set of vectors. And now you have a new star that's a Minkowski sum of two stars. So you can actually compute this term and get a star as the output. Another optimization you can do is, depending on what your unsafe states are, you may not really need to even take Minkowski sum. So if you're trying to maximize a particular direction over a set of states, and you know your set of states is a Minkowski sum, and it's only one direction you're maximizing. For example, if we have our spring mass system and we want to know the minimum position that can be reached to see if we've hit the wall, for example, we're minimizing one of the variables. So the minimum value of the first variable over the Minkowski sum of a set of states is equal to the minimum over this set plus the minimum over this set plus the minimum over this set plus the minimum over this set, and so on and so on. So you can really just do a minimum over each of the component sets rather than a minimum over the combined set of states. And so why is that useful? So that's useful if we're checking a safety property at each step. Because what's the change in this formula from one step to another? The first thing that changes is, first of all, this has to get updated because now you have another, it basically becomes a to I plus 1t. So this part will change. But the input part, everything stays exactly the same. You just add one more term, which is a to the it times the set u. So if you're trying to compute a maximum over this set of states, you just need to compute a maximum over the new input free part and the maximum over the one-step effective inputs, and then everything else you already had from the previous step. So that speeds up the computation a lot. If your set of linear, if your safety condition is not just a single linear constraint, you really want to create the combined generalized star set, and then you have a set of linear constraints. Then you add your safety condition, which is another conjunction of linear constraints, to the LP and check if it's feasible. However, you could take out the first condition from that conjunction of linear constraints that defines your unsafe states and do the same type of optimization, because until this set of states satisfies the first condition, it's not going to satisfy the conjunction of all the conditions, right? So you can still use this as a necessary check in the case where your safety condition is not a simple linear constraint. So what does this look like inside the LP? When you do this Minkowski sum, you end up getting a combined set of linear constraints that looks something like this, where again we have the current variables x and y. Alpha 1 and alpha 2 here, I believe, this is x naught and y naught, so the initial states of the variables. And now at each time step, you'll add a new variable, u1 and u2. In this case, there's two inputs for the inputs to use at that time step. And these three parts are the basis matrices for the three things that I've combined. So I have an input-free term and two time steps, essentially, now, where I have inputs. So this is the input-free term. This is the effect of the inputs at the first time step and the effect of the inputs at the second time step. What's interesting, though, is say you had a safety condition. So you added a linear condition over x and y here. And you solved a linear program, and it told you the LP was feasible. It actually gives you a solution as well. So it'll assign values to x, y, this is x naught, y, the initial states, as well as the inputs to use at each step. So then it tells you not just whether your system is safe or not, it tells you if you start in this state and you use this input at the first time step, this input at the second time step, and so on, you'll reach eventually a state, x and y, that violates your safety condition. So you get counterexamples out of this, which is sort of neat. So let me show you a demo of this. Let's do this one first. So this is an example. This is a benchmark problem. Was proposed 2 years ago. What it is it's a structural model of one of the components of the International Space Station. Right. So I didn't make up this problem. It's a 270-dimensional system with 3 inputs, and so there's it's sort of the standard x dot equals ax plus bu, and then there's a y equals cx. So there's an output that's a linear combination of all your state variables. And the property you wanted to prove is that the output is bounded. There's some bound for the outputs. So if I run this system using a tool called HighLow, which encodes this linear star approach, it runs fairly quickly, and it told you that error modes are error modes are reachable at this particular point in time, and it produced a counterexample file from the solution to the LP. And this was done in about 2.5 seconds, so very quickly on a 270-dimensional system. This counterexample file then contains the initial set of states that you should use and the inputs you should use at each time step. So let's take a look at that. So actually running the counterexample took probably about a second as well, but this is what the behavior looks like. So what is this? This is time is on the x-axis. The y-axis on the top here is the projected state. So I mentioned the safety property is that one of the outputs is bounded. The output is a linear combination of the states. So initially you start at this state, and then the output will change over time. This is the violation that you're trying to avoid. When you ran this system from the proposed initial state and using the inputs that the tool output using a high accuracy simulation external to HighLow, you got this path through the system, and eventually you reached a state that was unsafe. Furthermore, this is the 3 inputs of the system. So this is an output of HighLow. It tells you at each point in time you should use which input for each of the sort of 3 input values you have. So you can see it's a very complicated set of inputs that you end up having to use to show this violation. So in fact, if you held these inputs constant, you wouldn't get a violation from this set of states. And if we tried to find this counterexample another way, for example, there's falsification tools that try to do some essentially stochastic simulation, so it's like smart Monte Carlo simulation. We ran those tools for 4 hours, and they didn't find this counterexample. And if you think of what would it take to do some sort of exhaustive simulation, right? If you wanted to really just try all the combinations, how many would that be? Well, so this is a 270-dimensional system. So each of the initial values is an interval. So you have 2 to the 270 initial corners to start out with. So 2 to the 270. But then you also have to take into account that these inputs change over time. So if you wanted to consider all possible combinations of inputs, at each point in time, there's 8 sort of possibilities because there's 3 inputs, right? So it's a cube. So at each point in time, you have 8 choices that you would have to try. And how many choices did you make? Well, you made 1 at each time step, right? So this is over about 13 seconds. So you have to add 8 to the 13 seconds divided by the step size. The step size is 0.005 here. So if you compute that, you'll figure out what's the exhaustive number of simulations you would need to do to guarantee that you would find this counterexample. I put this into Google, and it doesn't compute an answer. You have to use like Wolfram Alpha or something else to actually do this number. But it's a very large amount, particularly because of the inputs. So we're happy with this result. So I'll show one more, which is the spring mass system. So we had the, let's open this with Emacs. So the spring mass system I had before, oops. Okay. So this is the spring mass system defined in HighLow. So HighLow it's a Python-based tool. It's actually like a library. So the model is defined in Python as well. So if you want to define the model programmatically, you can do that. The important parts here are I just have a parameterized function that makes the A matrix for the system depending on the number of masses. Then you define the settings. So here I'm using this interactive plot mode. So with HighLow, you can see the reachable set of states as the computation's going if you're using this interactive plot mode. And I chose the X and Y directions and then a couple other settings that don't matter as much. So there I chose the sort of one-dimensional or sort of one-mass system. If I step through this system, you can see what the reachable set of states looks like. So this is what was expected. You have this rotation around the origin. If I increase the number of dimensions, like 2, again, you see this sort of same pattern we had seen before, where now it's, there's 16 possible values, I believe, and you're getting the outer approximation of that. So that's sort of neat. And the question is, how high can we go, right? So each mass adds 2 dimensions to the system. What's our computational limits, right? So I've done this ahead of time, so let's try a 5,000 mass system. So this corresponds to 10,000 dimensions. Now, in order to do this, I'll disable plotting because I don't want to plot the system. Plot none. And so how do we know the system is correct? Well, this is what we'll do. We'll add, there's an error condition that's added to check if the value of x0 is less than -1, which corresponds to the first mass sort of hitting the wall. So this one takes a little bit longer because it's a 10,000 dimensional system. There's no inputs in it, so the sort of LP doesn't change over time. But eventually the sort of computation starts, and it's stepping through at each step and checking if that error condition is violated. This one was violated at time 16.3. Again, it produced this counterexample file. If I have the counterexample file, I can plot it like I did before, where you just see 1 dimension. But you can also plot it in 2 dimensions, so it's probably more intuitive because we were used to looking at these phase space plots. So let's do that. So the counterexample will define the dynamics as well as define the set that you should start with. So here I'm just going to change the plotting by defining the x dimension and the y dimension. And so here's the simulation, right? So we started out in one of the corners of the state space. Again, there's 2 to the 10,000 corners, and you pick one of them. You simulate for some amount of time, and notice that now the value of the position reached -1, which was our violation. So this was indeed a violation. To sort of gauge the accuracy, because I think there were some questions before of am I using floating point or intervals, and so I'm using floating point here, right? So that's how you can get more speed out of it, but you also don't want to lose accuracy. So one sort of gauge for accuracy you can use is when you solve the linear program, you have values of actually your start state and your predicted final state, right? So what you can do is you can run a high accuracy simulation after the fact and compare what does the high accuracy simulation say that the final state is, and what did HighLow say the final state was supposed to be, and look at the difference between these 2 states and sort of gauge if it's accurate enough. And so in this case, it can compute that the sort of relative and absolute errors are very small in this case. So likely this counterexample was an actual counterexample of the system if you trust the high accuracy simulation, right? So okay, so that was using linear stars to do verification of very large systems with over 10,000 dimensions. We're working on doing more, but this is sort of around the order of magnitude that we can currently handle. It sort of gets tricky once you go over 10,000. The reason is if you look at memory consumption, so this matrix exponential is going to be a 10,000 by 10,000 matrix. And if you use 8 bytes per entry, you're around 800 megabytes. If you were to go up another order of magnitude to 100,000 dimensions, you would end up having, instead of 800 megabytes of RAM needed, you would have like 80 gigabytes of RAM needed. So that exceeds what my laptop has, right? But there's methods to get around this, and we're sort of working on it. But it's sort of an active area of research. So I'm almost done. There's a couple minutes left, but I wanted to mention that I sort of focused on this time elapse operation, and certainly that's an important operation. Certainly the dimensionality of the system makes a difference, but it's sort of hardly the only concern, right? So there's systems I can define that have 4 dimensions that are linear, but have very complicated discrete switching. Or not, it doesn't even have to seem that complicated, but because of state representations and how discrete post works, you run into trouble on those systems too. So it's not just about continuous scalability. Discrete scalability plays a big part as well. I didn't talk too much about safety between time steps. There's a reference I can give you for that if you want to see. It's basically bloating. So you do a fixed time step, and then you bloat by a certain amount, and then you're guaranteed that between time steps you were OK. mode invariance. So we're tracking a set of states, and what happens if part of that set of states leaves the invariant? So what you want to do is you want to remove that from the set of states you're tracking. So that corresponds to taking intersections of states. So you can imagine you have a zonotope that's nice and symmetric, and now you're chopping away a portion of it. It's no longer going to be symmetric, so that's a concern. If you do research in this area, you can see that each of these things, there's papers on sort of optimizing this operation or doing it better than someone else does. So discrete transitions. So I mentioned you can do aggregation. You want to do a union operation on all the set of states that had intersected the guard. But exact union is hard for these representations that are, for example, a linear star is necessarily convex. The intersection over time is not convex, so there's going to be error introduced. So there's approaches to handle that, looking at resets, and finally looking at termination. So all of these, so far I've given it a time bound, but you can imagine if you sort of go back into a set of states you've already computed, you would like to detect that and say that you're done. So termination checking in high dimensions is sort of hard. So the last minute or so, or a few minutes, 9 minutes, I just want to talk briefly about various tools that exist for reachability analysis. If you're doing research in the area, I think it's sort of important to look at what the state-of-the-art tools are and what are their limitations so that you know where you can make a contribution, right? So SpaceX is a tool that can use support functions. I think there was also zonotope support at some point for this too. So the class of systems it handles are also linear systems or refined systems, basically linear plus a constant term. You can also have inputs. You can have non-determinism. It's not SpaceX the company, so that's confusing. The tool was around before the company was too popular, but it's SpaceX with an E. And in Google, you have to write hybrid systems tool before you get their site. But it's out of Verimag, so it's a big group. What's nice about SpaceX is there's this nice model editor for SpaceX. So the way I described hybrid automaton, it was sort of visually, but then you saw in the HighLow, I used a Python file to describe the hybrid automaton. That's not too nice. So in SpaceX, you can drag and drop modes, connect them with conditions. Furthermore, you can do hierarchy. So you can define a hybrid automaton that defines the motion of a vehicle, and then you can say this is type of vehicle, and then I have vehicle 1 and vehicle 2 and vehicle 3. These are all instances of this vehicle. And you can do variable renaming then. You can say that my x1 corresponds to vehicle 1, whereas x2 corresponds to the position of vehicle 2. And so you don't have to represent everything as sort of a flat hybrid automaton. So the editor is very helpful, and the tool is very powerful as well. There's a tool called FlowStar. So I've been focusing on linear systems. If you're interested in nonlinear systems, there's Taylor model-based approaches that do sort of validated integration with sets of states in order to do flow pipe construction. And these ones you can also do basically have discrete transitions as well. And it'll do conversions from Taylor models to template polytopes, I believe, or template parallelograms is the way it works to do this intersection operation. And again, you can visualize the output. If I'm using nonlinear systems and I have more than a few dimensions, it's sort of a good one to try. I think Xinchen said recently they've done a 200-dimensional nonlinear system, so over a course of a few days, but it's still sort of a nice result. HighLow is my tool, so I like HighLow. You can go to this website if you want to take a look at it. That's the one I had been using, or a version of that specialized for very large systems. You have these nice outputs you can get. You can produce outputs as the computation's going on for debugging. It's kind of slow if you have a very high-dimensional system, but nonetheless. You can also produce an image when it's done, and you can also produce videos too. So there's some YouTube videos on my website if you want to look at those, seeing how the reachability computation evolves. So it's kind of neat. And finally, there's many other tools, obviously, right? So there's the Acumen tool as well if you want, and many research groups have their own tool that they add their methods to. So I don't want to say this is an exhaustive list, but it's sort of a nice list to start out with. So something you might get frustrated if you're working in the area is the formats of the tools don't match. There's not a standard hybrid automaton input format. And so that's what I have this HIST tool a few years ago that was designed to help with this problem. So HIST takes SpaceX XML as input, so you can design your language using their nice visual tool. put it into HIST, it'll read it, and then it can output FlowStar, HiCreate, DReach, HighLow as well, simulator, back to SpaceX as well. So it'll save you time. It doesn't do parameter tuning or anything like that, so there might still be manual work. You output to FlowStar, but then you have to change your time step or something. But it's much sort of, I guess you have less errors than if you did the conversion manually. There's more advantages to HIST as well. So it's nice for syntactic translation. There's also model transformation passes. So sort of an important one is hybridization. So I described how to do reachability for linear systems and very large ones. But if you have a nonlinear system, this doesn't help you. So you can actually use HIST to do a hybridization transformation. What that'll do is it'll turn your nonlinear system into a linear system with inputs, where the inputs bound the error between the linear system and the nonlinear system within a certain domain. So then you have sort of a series of domains where you have sort of these piecewise linear systems with inputs. And now if you do reachability on your linear system, you can guarantee that that contains all the behaviors of the nonlinear system. So that's sort of neat. There's over-approximation error, but this is implemented in HIST, along with a lot of other neat transformations. Here's some general advice that I have from my experience in using reachability tools. When you design your system, simulate it first, right? So if you're using SpaceX, you can use HIST to output to a simulator and then look at the trajectories. And then the reason you do this is because if you're doing things manually, they're probably incorrect the first time. So if your simulations are nonsense, it's very hard to debug things once you're in reachability tools as to what's going on. Is it really the system's unsafe or my model's just completely wrong? And sometimes specifications can be very easy to violate. So why are you using reachability if you could run a simulation from the center of your set of states and it becomes unsafe? So it's sort of overkill to use reachability for that purpose. Don't start with the full system. So I've seen this a lot for industry where they want to use SpaceX, so they model their whole big system in SpaceX. They spend a lot of time and they hit run and nothing happens, right? So start with a small system and then build it up incrementally over time. And so that'll give you a gauge of actually, for research this is good too because it tells you where the bottlenecks are. I added one block and I can no longer do reachability analysis. So what's the fundamental reason why? That's an important research question. Simplify it until it works, then make it incrementally more complicated. Shrink the uncertainty. If you have a large initial set of states, shrink it down. Shrink down the inputs, make it a deterministic system first to start out with. And finally, shorten the time bound. So a lot of these tools have errors, and the errors accumulate over time. And so if you try to do a very long time bound, it'll tell you that the error sort of got too large and the tool quit. So shorten it down to a very small, short amount of time. So if you have a system where it's a very short amount of time, a single point, no uncertainty, the tools should work and sort of work up from there. There's a reachability tools competition that we started this year. So this was trying to compare different tools. This is associated with the ARCH workshop, which is Applied Verification for Continuous and Hybrid Systems, which is a neat workshop where actually people can submit either benchmarks or sort of benchmark results. So if you have a problem you want to solve but you don't know how to do it, you can submit it to them and then maybe other members of the community can look at it. So they tried to do a competition this year. It happens at CPS week, which is in April every year. Here's the sort of two references for both the linear continuous dynamics category as well as nonlinear dynamics, and I think there was a few other categories they had here. So it says it's a competition, but this year was more of like just try to get everyone to use the same models the first time. So we'll see what happens next year. I encourage you to also participate in the competition if you want. OK, so that's it. My review is basically, we want to formally verify hybrid systems using this method called flow pipe construction. And flow pipe construction critically depends on the certain set operation, so it's important to look at data structures for sets. So the three that were sort of important were zonotopes, support functions, and generalized star sets. But then I only covered one piece of the problem. There's also discrete dynamics I didn't really mention, or nonlinear ODEs. I didn't talk about those at all either. So. OK, so this concludes my talk. Thank you.
Thank you very much, Stan. Any questions from the audience?
In order to deal with errors, you have this input that, this U that represent the input. But the problem is that when you run for, you make a lot of steps, you get this very big input data for each instance. Is there some way to to avoid that by introducing the noise at the level of the linear system?
No, it's an interesting question, right? Instead of having nonlinear inputs, you could have nonlinear, the matrix, the dynamics matrix could be nonlinear. There's some methods that work with that. I don't have a definite answer for you. I would imagine sometimes it could help. Yeah. But there's, I think Cora, which is another tool for reachability analysis from TUM Munich, they can handle these uncertain matrices as well. But I don't know if it's useful or not. So. And so the other thing that's interesting, you said you add errors into the matrix, and then so these errors will accumulate. It's not always bad, though, because if you have a stable system, although you're bloating a little bit at each point in time, the stability can overcome the amount of error you have. So then you still, the reach sets will still converge, even if you're adding error at each step. So it's not always a problem. OK, thank you.
Since this is the last talk, very last talk of the workshop, thank you very much, Stan.
Thank you.
So we've come to the close of the meeting. Thank you all for being here. Special thanks to the speakers. I learned a lot. And we had actually several speakers mention that they have gone to many meetings and in new areas to them. So when they're full professors and very established in their career and they want to learn about a new topic, then they go to conferences and they talk to grad students and learn from grad students. And so I think that I personally learned a lot, and I feel that it was good advice from these other speakers that being comfortable with going to learn in any context, in any environment, is a very important thing for succeeding in your career in the long term. So many thanks to the speakers. Many thanks also to the participants that contributed to the great discussions. Some of the feedback has already come in, and it's been very positive. Several people commented on the organization. And so I would really like to thank the people that have been involved in the organizers. And I sat down to make a list, and it turned out to be actually quite a substantial list. So the organization included Professor Ueda and Professor Walid Goma from the Egypt-Japan University, who's not here for the meeting, but actually has worked quite hard to develop the school. Also, Mohammed Moussawi has contributed to helping us learn from previous summer schools that have been here at Halmstad and making sure that we do things in the best possible way. Louise Vendel from our communication department actually did a great job of keeping track of all the things that needed to be done and making sure that we get everything ready and creating many of the materials that we have here. There's also Maria Westerlund that has made sure that we have the lunches on time and they're the right lunches, and when the breaks were late, she actually stepped in and helped with that. We have 2 interns that have been very kindly volunteered or willing to be volunteered to help, Muhtasim and Victor, who have dealt with all kinds of things that have come up during the meeting. Little books, or the kind of gifts, were always provided on time by Muhtasim to me. Thank you for doing that. Who am I forgetting? I'm sure I'm forgetting somebody.
Maybe you?
I don't need to thank me, but thank you. Let me see. It's we have had an excellent video crew that has been taking care of the recording and doing a great job of that. We had people from IT that came in and helped us make sure that we have all the connections that we need, Lotta and Piu in particular. And the staff from the restaurant, Spiro's, has also been very active in checking on us every now and then and making sure that we have coffee. I also want to mention, I may have missed some people, so I apologize if I've done that. Masuma has also been very central. She's a postdoc working in Halmstad with Mohammed and myself. She's been taking care of a lot of the organization work and putting all the materials together as well. She wasn't able to be here for the entire school, but she's put in a lot of work in making it happen. There are a couple of people from our department, Jessica Rosenberry and Stella Erlandson. They've also been involved in the early stages and making sure that we have everything in place to make this happen. So I really want to thank them all on behalf of all of you today. I'd like to acknowledge the support that we have from different organizations. For example, Halmstad University has been very supportive in making this event happen, and in particular our Dean, Magnus Clarine, I should say. As well as the KK Foundation, which supports several of our research projects. And also my own time has been supported in part by the US NSF Foundation. Yeah, and with this, I think I'm done. So thank you all for being here, and I look forward to seeing you again in other contexts. Thank you.